Okay, so well, it's always great to be here in KL at Hack in the Box, and it's my favorite conference ever. So end of the year, time is nice, relaxed, and always with good friends. So I hope you've been enjoying the show so far. What I'm going to talk to you for the next 1 hour is some R&D that I've done with browsers, and I began wondering as to what the hell is so wrong with browsers. I mean, there's many things wrong with browsers. Right? There's everything wrong with the internet anyway these days. But kind of figured browsers are becoming the next desktop, and there's a lot of things broken with browsers. So figured I should do something about it, and tinkered around and came up with a proof of concept tool right now called Teflon, and hopefully it should start some directions in building a better security model for browsers. So with that being said and done, a quick introduction about me. My name is Saumil Shah. I live in India and do a lot of security monkeying around. If you want to search, just Google Saumil and read up about stuff that I've done, if it exists on the internet. So what I'm going to talk to you about is, what are the next attack vectors for browsers? Thanks to the whole Web 2.0 nonsense, the browser is becoming the desktop of today. There's a lot of similarities and analogies if you start comparing browsers with desktops. I mean, you have a desktop computer, you download code off the internet and run it. Great, we don't trust it, right? We just, as long as it's free, we download it, we install it and run it. On a browser, it's the same thing. You point a browser at a website, stuff comes in and it runs. So what's the similarities and what are the next attack vectors on browsers? Now, there are classic attack vectors like cross-site scripting and whatever have you. We're not going to talk about that. That's all what I technically call user-land browser attacks. We're going to talk about hardcore browser exploits, stuff that blows up the browser and stuff that gets attackers control of your instruction pointer and so on and so forth. So with that, browsers, like I say, are the most fertile target area for exploitation. What makes browsers really juicy for attacks? Seen any average browser, you go to your aunt's place and look up, see what the browser looks like. Today's average browser looks like this. This is what it is. Everyone has like 80 different system tray icons and 30 toolbars and browser helper objects and all this. I mean, these make fertile grounds for attacks. You can blow up toolbars, you can blow up browser helper objects, you can blow up media handlers, you can blow up ActiveX objects and whatnot. And these are ripe with bugs. These are ripe with buffer overflows, with integer overflows or whatever have you. And all of a sudden, exploiting a browser has become very easy. And I'll show you later on that techniques like randomized stack or non-executable stack, they don't stop browser exploits. I mean, browser exploitation is a lot of fun. It's pretty swift and easy, and there's like new browser exploits coming out every week. Some of them are deadly, some of them are with some insignificant stuff. But before I get into that, let's think about what is at the heart of every browser. What makes a browser work? Inside every browser, there's like one central component. Anyone? Okay. It's this. It's a document object model, right? That's what a browser is. It's an HTTP client with a renderer. It loads in HTML and displays it on your screen. And it lets the user click around and make a new request and loads more HTML and displays it on your screen. That's what the damn thing does. Well, HTML displays fine, but browsers also have a wonderful little thing called JavaScript built into them. That's great. Now the software that I want to exploit has an interpreter at my disposal. I can program it before I can trigger an exploit. So what happens is you have a lot of user-loaded content through HTML, which comes and gets displayed and rendered on your browser. In addition to your DOM and JavaScript and HTML, browsers have many plugins. There's ActiveX, there's MIME handlers, browser helper objects, there's stuff like Flash, and now the whole environment is getting richer and richer. You have all this Ajax shit that's going around, various unaudited toolkits like Dojo or Scriptaculous, and they're being mashed up everywhere. And down below, at the plugin layer, you have the browser should be everything type of model, like Google Gear, Silverlight, Adobe Air. They want to make the browser access your host operating system, pull up databases, and make the browser stand alone. Well, that's great. That just made the exploit area very, very fertile. So if I were to compare the architecture of a browser with the architecture of any desktop operating system, it's very, very similar. You have stuff that happens in a browser and stuff that happens in a kernel. It's all the same. If we were to draw a diagram, we can draw something like this. The browser is analogous to an entire operating system. Your DOM layer and all your plugins in the browser are very similar to drivers and kernel. So, if I were to equate things, the DOM can be equated to the kernel. Your plugins and extensions can be equated to drivers. Now, what happens on a desktop if you exploit a driver? What do you get? You get control of the entire kernel. So what happens when you exploit a plugin on a browser? You get control of the entire browser. That's what happens. And on the user land layer, you have user-loaded code. The user-loaded code can access the kernel layer via system calls. And in the browser land, you have what I call the equivalent of browser layer system calls as these tags. You have the object tag, you have the embed tag, and things like these. Using an object tag, using an embed tag, you can reference any area. It's going to be hard to point, laser point this way. No, this is not going to work. Okay. Using an object tag, oops. How can I draw? I can't draw. So, using an object tag, you can reference any plugin in the browser. You say object CLSID is equal to some COM component, it will load up the LinkedIn toolbar. You say embed source is equal to something.swf, it will load up a Flash player. Object file is equal to something.mov, it will load up QuickTime. So using these HTML tags, you can create code that references any drivers. Now what if this driver has a vulnerability? You can deliver the vulnerability entirely through through HTML and cause a browser to blow up. So that's what we're going to see. Here's an example of what I call as a browser syscall. Let's say you go to apple.com QuickTime, you want to see a lot of QuickTime trailers. There's HTML being loaded in. This HTML gets loaded in the browser's DOM and everything, that's fine. Inside this HTML, you have calls like, you have HTML tags like object CLSID equal to blah, blah, blah. This will load up the QuickTime player. You're trying to load up a QuickTime movie inside a browser. So QuickTime player will be loaded up and displayed in the browser. Internally, what happens, a QuickTime instance is created and runs in the same process context as the browser itself. So if QuickTime blows up, you get control of the whole browser. Now, exploiting a browser is pretty easy. You have many, many tools at your disposal. You can create a browser exploit entirely using JavaScript. So now let us say you want to break the QuickTime player through a browser. You want to send 100,000 bytes to the QuickTime object. You don't have to create a payload of 100,000 bytes and push it to the browser. You can create a little JavaScript loop saying, instantiate a variable, pack it with 100,000 bytes, and then drop it on your own foot, and it will blow up the QuickTime object. What's more wonderful is you can preload the process memory exactly the way you like. This does not happen when you're exploiting other software. If you're exploiting a war FTP daemon, you can't say that load up 2 megabytes of NOP sleds and shell code in the memory and then go exploit yourself. With a browser, you can. You can create JavaScript that loads up the heap memory exactly the way you like, thanks to guys like Alex and Mark and other researchers who worked on heap feng shui and stuff like that. You can spray the heap, you can load the heap exactly the way you want, and then let your exploit return to the heap. This makes browser exploiting a lot of fun, very easy. Techniques like address space layout randomization, non-execute flag on the stack canaries, these things don't bother us. What we can do is we can map the memory just in time and then jump into it. Okay, so quick theory on how browsers get exploited. Here's what you do. You have a little JavaScript loop with which you take large NOP sleds, like 1 megabyte NOP sleds, attach your shellcode at the end of the NOP sled, and then make multiple copies of this NOP sled and shellcode all over the heap memory using JavaScript arrays. And then you trigger your exploit condition. Your exploit takes control of EIP, but you can't return to the stack or anywhere else, so you say just jump into the heap, return to memory that was not initially there, but it's populated at runtime and things work. This is how most browser exploits work. So here's a quick summary of how it happens. Here's a diagram, rough diagram of the browser's process view. You have, let's say somewhere down in the stack you have an overflow. Before you actually trigger the overflow, what you do is you run some JavaScript in a loop and spray your shellcode blocks all over the heap. You spray multiple instances. You don't care where they are. As long as they occupy large regions of the heap, you can pick any address at random and straight away land in the heap. And that will work. So as long as you land in any of these orange blocks that you see on the screen, you're fine. Now once your heap is set up, you trigger your exploit, say overwrite a stack frame and overwrite a saved EIP or an exception handler and whatever it is. And instead of returning back to the stack as conventional exploits go, what you do is you jump into the heap. You return into one of these orange blocks and then you win. So that's the theory of browser exploits. We'll see a couple of examples, and then after seeing a couple of examples, I'll introduce you my research, the tool called Teflon, which is right now a browser plugin. It's implemented in Firefox, and it's my attempt to try and stop these kind of exploits from occurring. Then we'll talk about some pros and cons and features and limitations of Teflon and end the talk. All right, so now let's do some demos. Let me show you an exploit. I'll take a classic exploit. It's a Firefox and Windows Media Player exploit, a year or a year and a half old. If you have Firefox on Windows and you launch Windows Media Player with a very large file name, then the Windows Media Player plugin will crash and it will take Firefox with it. We'll see how we can create an exploit like this and then break it, and then we'll see how Teflon works and all that stuff. So, if time permits, we'll show another IE exploit. But everybody beats up on IE, so I didn't want to beat up on IE today. Okay, here we are in my Windows VM, and start Firefox. So there's Firefox. What I'm going to do is take a sample exploit code. Let me show you the code. Let's see what happens. Let's open up a more readable terminal. Can everybody read this stuff? That's fine. So I have a simple Firefox exploit. Here's an HTML file. Basically, we need to create a 2200 byte buffer of A's and then put WMV at the end. And if we create an embed tag and launch Firefox, once Firefox renders this embed tag, it will blow up and we will cause Firefox to crash. We will get control of EIP and all that fun stuff. So let me run this and let's see Firefox crashing and burning. Okay, so here's Firefox. I've started that web server. Let's load it up. Just pointed at the web server, and there it goes. Firefox crashes. Okay, let's do it again, and this time we will attach a debugger to it and see what happens. So here's the debugger. Attach this to Firefox. Don't worry about this debug shit. I'll walk you through it. Okay. So there we are. Launch it again. Wait, I need to run that web server again. Okay, there it goes. Crash. Now let's look at the debugger. And debugger is waiting at an exception. If we proceed further, basically we get control of the instruction pointer. We get EIP equals 41414141. For those of you who took the exploit lab yesterday, you know what this means. Basically, we can put the shell code and win it. So let's do that. Let's actually convert this into a practical exploit and make it work with shell code. The problem here is where you want to jump after you get EIP control. You can't jump back into the stack. You can't jump through registers. You can't jump into a DLL. But what we're going to do is we're going to populate the heap memory, load up our MOP sleds and shellcode in the heap, and then jump into the heap and win. So I'll show you an example of such a heap spray. Let me run Firefox again. And let's see how we can convert this crash into a real working exploit. So here's a final exploit that is pieced together. It's the same thing. I mean, what we're doing is we're still doing the same trigger, 2200 A's and triggering it, except we are now jumping to an address which is in the heap, address 05050505. It's an address picked at random, but at this address, you will find a very large NOP sled, which is created by this JavaScript loop. And then the NOP sled and shellcode are sprayed 50 times over the heap. And that's easy enough. And this will break, this will cause our shellcode to run. And here's the shellcode, also included with the HTML, nicely written in JavaScript. And the shellcode runs calculator. It is, the next hello world of all shellcode. That's calculator. So let's run this and see Firefox turn into calculator. Okay, there it's running, and now let me hit this. First attach that debugger. There we go. Run it. Here we are getting an exception. If we look at the next step where we're going to jump to, the next address we're going to jump to is at 05050505. For those of you who are technically inclined, if we look at the memory occupied at 05050505 right now, you have these NOPs, all these NOP codes. And if I proceed, at the end of this NOP sled, you have the shellcode. This is return to heap. So if I now proceed further, you get a calculator. So voila, your Firefox stands exploited. We get a calc running, and I mean, instead of a calc, you can do anything. You can now have a Trojan downloaded and make this a part of a big botnet and whatnot. So Firefox is owned, and this is how browser exploits work. How do you stop these things? How do you prevent browser exploits? I have not found a satisfactory answer yet. If you think of antivirus stuff today is only good for slowing down your computer and playing old DOS games. Does nothing else. Get a faster computer, it still feel like a 386. It's nostalgic. Why is antivirus so pathetic and ineffective when it comes to stopping browser overflows or browser attacks? These attacks are not like your traditional classic exploit attacks where the payload has to go in with a very large buffer and the shellcode and everything goes together. I have JavaScript and I can build up an exploit entirely with JavaScript. I can obfuscate this, I can encrypt this, I can build this exploit up in parts. I mean, simple things that I've done have also fooled some antivirus programs. Let me show you. For example, if I just take this exploit and I revise it a little bit. Here's the same exploit, but instead of creating an embed tag in one line, I can create an embed tag using just 5 cuts of a string. I can piece together an embed tag with something like this: document.write s1 plus s2 plus s3 plus buffer plus s4 plus s5. I mean, simple stuff like this will fool antivirus programs. There is no signature that you can apply. And I'll show you some code pulled off from Chinese malware sites, which is unique every time you load the code. Every time you load the code, there's new JavaScript being generated on the fly, and there are actually encryption keys being sent through cookies. So JavaScript gets loaded, key comes in through a cookie, it gets decrypted, and then it blows up. So there is no way you can signature these things, and therefore there is no way these attacks can be effectively stopped unless you build in some granular security inside the browser. So that's the point which I'm trying to make. So the problem is, exploits can be delivered by JavaScript. They're built up on the fly. They're actually delivered locally because JavaScript gets loaded on your machine and then exploits your browser. It's not a remote exploit at this point. It's just remotely loaded and locally exploited. And you cannot signature this. So nothing really, you don't know if you have an exploit at hand unless everything fits together at the last moment. So you have to be in the browser to be able to stop these type of exploits. So I already ranted about the effectiveness of antivirus software, and I'm not going to slam on antivirus anymore. I guess because part of the antivirus guys sponsor this conference. I can't really piss on him too much. But what I'm going to talk to you about is my attempt of protecting against browser overflows. Ideally, the code that I've written should be built into the browser kernel itself. Right now, I've just implemented it as a plugin, but I wish there is some standard coming up and this code gets built inside a browser. So, what are the objectives of Teflon? What I like to do is, sitting inside the browser, I can inspect the DOM every time it changes. I can inspect DOM mutation, and every time the DOM gets changes, I can take a look at it before it is being rendered. Slightly slow, but not that terribly slow. If I see an offensive vector, if I see like a malicious object tag or an embed tag based on some signatures that I know, or something like, this object tag is taking up like a 20,000 byte parameter, I don't want that to happen, I can rewrite the object tag before it gets rendered, or I can kill it, or I can replace it. And thereby, I can block these type of browser attacks from being rendered. So all I need to do is prevent malicious browser system calls. I'm not going to disable JavaScript. I would like rest of JavaScript to run. but just parts that create these malicious tags, I want to stop them. Current iteration of Teflon is 0.2. I'm soon going to open source this as soon as I get back home to India and take a week's worth of rest, which I haven't had in a long time. And currently it exists for Firefox 1.5 and 2.0. I'm working on Firefox 3. If anybody of you has any experience in coding Firefox 3 extensions, I would welcome your help because the Firefox 3 documentation is pathetic. It sucks. So all you have to do is reverse engineer other extensions and build it yourself. So it doesn't matter how cute that orange fox looks if the documentation is broken. And eventually I want to have a plugin written for Internet Explorer as well. Right now what I'm doing is simply replacing these malicious object tags with a big red div tag. So there's a big red bar on your browser which shows you something bad would have happened if Teflon wasn't there. The rest of the stuff will run. And you may recursively obfuscate it anytime, any amount of times you like. You can create nested loop of 5-6 iterations, and the 7th iteration may cause the exploit to come together. It doesn't matter. I mean, with Teflon you can block these things. So let's see the same exploit in Teflon, and then we'll see how it works with packed and obfuscated JavaScript and other stuff. Right. So, coming back here. Let's take the same exploit and let's, let me run that web server again with the basic exploit. And this time we will turn on Teflon and see how that works. So there goes Firefox. Okay. Here, if you look at the bottom corner of Firefox, you have a little Teflon thing. I'm very poor at user interfaces, so even this type of a zoom interface took me a day to write. I'm a command line guy, I don't like these GUI things. So, well, what I'm going to do is you click it, Teflon turns on, and now it's actually it's actually a Firefox plugin. There's Teflon. Another thing I want to do is also start up the JavaScript error console. So Teflon writes to the JavaScript error console. So we'll track these events and see what Teflon says. Okay, now let's point it. Same Firefox exploit, Teflon turn on. Okay, we don't get a cal. It says it just replaces it with a big red bar. And let's look at the JavaScript console. Over here, try and see if I can increase the font size. Okay. Let's see if I can. Can't increase the font size. But over here it just says that whenever Teflon encountered that big object tag, it replaced it with a it just replaced it with a div style is equal to border thick solid red. And this is just my mark to show that something was replaced. It could just be silent about it and log it to a file or whatever have you. Let's do a view formatted source. And let me show you what the rendered source looks like. Okay. So here's the rendered source. Div source is equal to all this. So everything else remains the same. The object tag just got transformed into a div tag and with a solid red border. Okay. Now let's take some more complex cases. I mean, this is all well and good. Here's a simple exploit. There are many JavaScript obfuscators. I mean, I tried a couple of them. There's one called /packer. It's available on a site called dean.edwards.name/packer. All you got to do is paste in your JavaScript and it will create a fantastically obfuscated form back for you. There's another one called script asylum encoder and decoder. When you pack your JavaScript in this manner, what happens is you get this big packed and encrypted encoded JavaScript. It will decrypt in memory and then render your exploit. And this is enough to fool most antivirus programs. Let's see how Teflon fares against both of these. So, here. Here's the packed version. So the same simple JavaScript code now got transformed into all this. We have this hideous JavaScript that's impossible to read, but it's like eval and blah blah blah. All your variables are broken up into tokens, and your data is over here somewhere. But basically, what happens at the end of this, you will have your original code constructed back, and that will run and own you. So let's run this. Okay. Now, let's run this without Teflon and see how it works. Reload this. There you go. It blew up. It decoded itself and then rendered the exploit, goes up. And now let's see how it fares with Teflon. It's obviously not going to work, because otherwise I won't be standing up on stage doing a demo. Okay, now let's do this. Restart the web server. And sorry? Oh yeah. Finger error. There. Thank you. There we go. Now you can see in the Teflon messages, first what happened is the big unpack happened, and you have your original JavaScript being decoded after being unpacked, and then Teflon kicks in. So you have one more iteration, but that's okay. Let me show you a rendered source, new formatted source. So this was the original JavaScript, which was all heavily packed and obfuscated. Once this ran, it unpacked my original exploit script, and then we have Teflon kicking in after the second unpack. So normal stuff runs, but malicious stuff gets stopped. Let's try another instance. Let's try the script asylum encoder and decoder version. So here is the encoded shellcode with script asylum. This makes it even worse. I mean, you have document.write, unescape, everything's always gobbledygook stuff. And to make matters more interesting, we say we'll do both. We'll do packing and encoding, like double layer obfuscation. So FF both is both packed and encoded. So first it will get decoded, then it will get unpacked, and then the exploit will try and render itself. I mean, this is impossible for any AV or any IDS. IDSs are a joke, by the way. In all honesty, you have an IDS, it will be nothing but dust, blink and lights. Nobody really cares. Every pen test that I've done, there's always this one pen test that you do every year where you bust everything and done. Some company always gives one like that. They'll have it all. They'll have firewall and IDS and, well, yeah, guess what? My big port stands showed up on your IDS, but nobody did it. Anyway, end of rant on IDS. So let's run this, and both doubly encoded and encrypted stuff. Let me just close Firefox so it will purge the cache and everything. And now, so let me turn on the error console there. Let's also turn on Teflon. And now, there it is, load it up. Now you see multiple iterations. So the first loop ran, it got decoded. It got decoded into the packer script, then it got unpacked into my original exploit. And then Teflon kicks in at this point. So let me show you the rendered source for this. So there you have the original stuff, that's all over here, both packed and encoded. It got decoded and resulted into this packed script. It got unpacked and resulted into this stuff. And then, so there's like the DOM mutated thrice, and the fourth time I intercepted it and stopped. So that's what it is. That's what Teflon does. Let me show you. I tested this out in the wild as well. I just pointed it at some various malware sites. There's one particularly interesting stuff that I found, which I copied. So here I showed you how Teflon fares against both of these. In the wild, I came across a site like www.qqq.cn. This will deliver you the latest malware whenever you browse to it. I mean, this is like big ass malware delivery engine. This gives you various iframes and 3 or 4 most current browser exploits. If you haven't patched it, or you have some vulnerable versions of toolbars or plugins going in, a visitor is going to get owned. And by the way, if you want like cool 0 days, go to this site and just grab the code coming in. Of course, be careful. Do it from a VM, which you can undo later on, but a nice source of picking up new stuff. And this was fantastically encrypted and randomized. I was amazed as the kind of work that is going in. I mean, without all it is the simple IE vector markup language bug, which came up last year, but it's delivered in this wonderful encrypted and randomized way. I mean, without Teflon, you'd get owned, but with Teflon, it works. Let me just show you instead of screenshots. So here it is, MS 07004. I mean, here's the code. If you reload it, you'll get different variable names every time, and all this stuff is encrypted or obfuscated. And then down below, you have all these various bit transformation functions of MD5 and bit to hex and whatnot. A whole lot of S boxes type of stuff. And here's the best part. Every time you load it, you get a new variable over here. You get a pass is equal to something else, and this will be used to decrypt all that encrypted shit. Every time it's something different. So you really won't be able to build up any signatures against this. And lastly, when this code does perform page, that's it. That's when the exploit triggers. Until you get to the last piece of the puzzle, you won't have any signaturable exploit in this guy. Let's run this. Let's load this up in the browser and see how Teflon fares against it. So here we are, and let me shut this down and clear the cache. Turn on Teflon, error console. Okay, so there we are, loaded up. It's blocked. We don't get a shell. Anyway, it's an IE exploit, so it won't work in Firefox anyway. But got intercepted and blocked it. And here's what Teflon detected. So once all that decryption happened, here's you can see class ID is equal to 100 something. It's referring to the IEVML object. Then you have all the shellcode over here, and then down here you have the body on load is equal to whatever, and draw your vector markup language tags and blow it up. If you look at the rendered source, I mean, the whole thing expands. This is the original stuff. The original stuff that got delivered with all the decryptor stuff built in. And then when it ran, it got decrypted into this. This is the decrypted exploit code. Shell is equal to one escape, and then you have all your heap spray stuff going on over here. So here's the heap spray code. There's actually same stuff lifted from Skyline's code. And then here you have all the HTML tags VML tags which will render you that malicious VML tag and blow things up. So this is what the state of exploits is today, and that's what I hope to stop with tools like Teflon. So with Teflon, all we get is a harmless div tag. So to put some closing thoughts to the work that I've done, I mean, Teflon, I'll admit, it's not super perfect. It's something that, I cooked it up. It's still version 0.2. It's not a very usable version. I mean, who the hell uses version 0.2 code anyway? But the whole world does with a damn thing called Google Chrome, I tell you that. So, buggiest bloody browser in the world, but half the world's using it. Why? Because it got launched with a comic book from Google. Anyway, you can see I'm a pretty bitter guy when it comes to browsers. I don't spare any browser. But the thing to think about with Teflon is, right now what I'm working on is how can we make such technology built into the browser, how can we make this work in practice? How would this happen? Maybe with Teflon you have a list of known malicious objects, something like Microsoft Killbit stuff. You just load it with known vulnerable COM objects or vulnerable ActiveX stuff or vulnerable object tags, and block these at the get-go whenever you see them. So existing vulnerabilities may be tackled. If you may also program things like you don't want to see object parameters more than a certain amount of bytes in length, and this may very well just blindly stop some basic buffer overflows that may come up in the future. Or you may have some fancy implementations like a website. When you load up a website, the web server headers will send a list of what is allowed on the website and what is denied. Something like, say, if you go to youtube.com, YouTube will send a header back saying the only object tags allowed on youtube.com are flash objects. So if you have any other object through some malicious iframe or something else, if you have anything else being rendered through the YouTube site, don't run it. And a tool like Teflon can obey these tags and enforce those policies for that website. There's a guy in Mozilla, Brendan Stern. I'm working with him right now. He's building a project called the Site Security Project that is mainly for the cross-site scripting and cross-site request forgery stuff, what I call user-land stuff. And he's developing a framework on how do sites declare what is allowed and what is denied. And something like Teflon can work very well with a site security project plugin, is that in addition to what JavaScript sources are allowed, the server will also transmit back tags saying what tags are allowed and what tags are denied. What I want to underscore is there's got to be some mechanism, some standard mechanism built into browsers using which websites or even users can control what tags can be rendered and what tags are to be denied. Some sort of syscall marshalling for browsers. So I don't know how this will work. I mean, there was something done similar. There was the whole P3P project, which sent a whole lot of privacy tags, but nobody obeyed them. It's history. Another limitation of Teflon right now is Teflon exists as a plugin. And I'm sure another plugin can come and unseat Teflon or hook below me and bypass. So ideally, this should be built right into the browser. I was hoping that the new browser standards by Firefox 3 or IE8 or even Chrome, they do something about security. Unfortunately, not much is being done about security. Only new things are things like web slices and mashups and tearaway applications and whatnot. So out of all these browsers, none of them have really thought too much about browser level security. Some future R&D directions. I mean, I've thought about this a lot, and maybe if you can comment as well. Is it possible to detect heat sprays in a process? Like, can we detect if the heap is being sprayed? I mean, somebody was telling me, why don't the browser have a mechanism to see if large amounts of heap memory are being consumed consecutively, raise an alarm and say, oh, there's a heap spray going on, I'm going to stop this. I also noticed that if you look at the heap memory after loading up a page from Flickr, it looks exactly the same. When you have 80 JPEG files being loaded in the browser's heap memory, it looks like a heap spray. There's no way you can distinguish between real content that is loaded. In fact, theoretically, you can even have JPEG files with large knobsleds and shellcode in them. So what you're seeing on your web page is a bunch of photographs, and each one of them is a knobsled and shellcode. The exploit can jump into one of the JPEG spaces and kill itself as well. It's possible. I just want to put it together for kicks. Here's a photo gallery that will own you without gaps. So there's some future directions. Maybe you can have signed JavaScript in JS, but I don't think that's going to go anywhere. That's pretty much what I had to share with you guys. There's this time left, so the floor is yours. I'm here. Any questions, any comments or thoughts that you may have, any criticisms, let's have it out. And Jeremiah.
You mentioned some of the limitations of Teflon. Are there any undesirable consequences from running Teflon that might impact the user experience? So, are there any undesirable experiences from Teflon? Teflon does alter stuff. I mean, Teflon right now, kicks in every time your DOM is mutated. So one thing is, yes, it may slow down your JavaScript experience a little bit. I have tested this with Gmail though. I have not noticed a huge performance impact. Sometimes, maybe it's because of bandwidth or what, but it's not, you can't feel that Teflon's loaded. But I must say, with Gmail, a couple of things have been broken, like a couple of sidebar things have been broken. This is because probably it may be using some advanced AJAX stuff and mutating the DOM where Teflon rewrote it in some manner. Right now what I'm doing, I'll share with you what I'm doing. I'm hooking all the DOM mutation events, and I'm especially paying attention to eval, document.write, and inner HTML. So whenever these things fire, I take a look. And if anything looks similar to a malicious tag, I rewrite it. So this may break some stuff. It doesn't break things severely, but I do need some JavaScript help. My JavaScript is very poor. I'm sure there's ways to inspect things seamlessly and stitch it together, but right now I'm just doing it in a clumsy manner. So yeah, I'm going to open source this, and contributions to this project are very welcome. Gmail is my test benchmark. My thing is, if it works with Gmail, it's going to work with everything else. Yeah.
So I was curious to understand how Teflon works, because it sounds like you've got some sort of signature that looks for bad behavior, and then you sanitize that, which sounds like antivirus, which you seem to have a rant against. So I want to understand the difference.
Yeah. So, right now, Teflon is, it'll stop something that you don't want on there. Right now, it's in a very simple state. I've right now told it that these are the kind of things that I don't want to see on a web page. I mean, object tags with more than 1,000 bytes in a parameter, or embed tags with more than 1,000 bytes in a parameter. I'm not super signature based. I don't say that block this CLS ID or block this CLS ID or whatnot. I can, now this is where the implementation part of Teflon comes in, is I want to figure out a nice practical way of not being bound to signatures, but detect that, okay, if these type of tags come in, I just don't want them. Tag types, extension types, or something like a declarative model is, if the website's telling me that no flash, this means no flash, everything else is okay.
Sure, but a bad guy site is just going to say flash is cool, right?
Yeah, I mean, if a website tells me that flash is cool, the website's owned. So,
but
there you are.
the attack's against your machine.
I'm sorry?
I go to
Yeah, you put up a
CNN.
site like QQQ.cn and tell me that all these malicious tags are okay. I can have something like this, is by default, just don't do this, allow only stuff. I mean, if it's a site like Gmail that I know of, say, obey directives from Gmail. If it's a site that I don't know of at all, just go blank and just have everything turned off. Have every type of a browser syscall, which basically boils down to object, embed, and a couple of other tags. Just don't run them. Only if this site looks cool, let's allow some things on there.
So the user decides
So
if
the
the site's
user decides.
malicious.
User decides.
Is that the right place to put the trust?
What choice do you have?
Okay.
I agree. I mean, I'm in the same debate. Some more thought needs to be put on this. But I'm with you. I want to avoid signatures at every cost.
So the other thing I wanted to discuss about, in the slide before you have, maybe there's a non-executable heap.
Yeah.
And I'm trying to understand what you mean by that.
Dino, you want to go for this explanation?
Vista SP1 made all the pages allocated by a heap, like a JavaScript heap, non-executable, whereas previous operating systems did. So, for instance, loading heap sprays basically were loading shell code directly underneath the JavaScript.
Right.
On Vista SP1 would not work.
Right. So we turned on DepNX, but like 25 slides ago, you said it didn't work.
I beg your pardon?
So in Internet Explorer on Vista, the DepNX feature is enabled. And it sounds like
If the application says VM alloc, give me pages marked read, write, execute,
Right.
it will be given. And that's the browser thing. Because NX just says basically you must obey the permission for the page.
sure, but in order to validate code or memory, you already have to have arbitrary code execution, right?
No, usually a plugin, like Markdown and Alex Sokorov attacks, basically.
Right.
Doing the same thing with Java.
So if you've got a vulnerable plugin,
Well, no, not vulnerable. You have a plugin that is insecure.
Okay.
Basically, because it is not careful about how it allocates memory pages.
sure.
But for instance, like allocating a Java class file, as well as make it read write executable, which is a big deal.
Just feels a little strange to me to say like these technologies don't work because people don't opt into them, right? It seems like it'd be more effective to evangelize people using the technologies.
Sure. I mean, if everybody did secure coding, we wouldn't be here.
Sure. Well,
Yeah, no, there are things like this. So I'm saying non-executable heap does exist. I mean, if I haven't played around too much with it, but these things would break heap sprays. This thing would break a heap sprays effectively. It's not as universal enough. That's all I'm trying to say. Anything else? All right. Well, thank you for your time and attention.